Do you see the screen? Are you able to see the screen?
Yes, ma'am.
Okay, good. So now the question is, earlier we had talked about what is how to discover a neutrino and what is the Reen's-Cowan experiment. Oh, I have not connected it. Okay. Reen's-Cowan experiment, how it discovers neutrinos. And basically it is a pulse and as a function of time. So if I do that, I do find one double pulse and then it is a coincidence pulse. And something like 25 microseconds, up to 25 microseconds gap, you do find another pulse. This is a 10 MeV gamma pulse. That is corresponding to a 10 MeV gamma ray, you have another pulse. This is what is called as a double pulse, famous double pulse in neutrino experiment. And I had told you, this is found, say something like 3 to 4 double pulses were recorded per hour. And they did an experiment for 1,400 hours. So this is a famous experiment done in Savannah River reactor, nuclear reactor. So this is what I had told you yesterday. Now, next question is, what is it that we had verified? So let me just tell you 1 minute. No, wait a minute. All right. So I have, I will show you that what we had talked about earlier was to say, I have a neutrino. How did I discover this neutrino? I said, it is not a neutrino, it is a nu bar. That is for our convention. So I said a neutron decays into a proton plus a electron plus a antineutrino is what I told. Now, yesterday, day before yesterday, after my class, people asked me, I had told you earlier that a photon is its own antiparticle. Pi 0 is its own antiparticle. A natural question then would be to ask, is neutrino its own antiparticle? So this is the question that we have to face, because all neutral particles except neutral particles appear to have their own antiparticles. But now this question takes its own way. I have to verify it experimentally. That is the next agenda. So I will just tell you about whether neutrino is its own antiparticle or it is a different particle. We have to verify that. So that is our next part in the series. So that is to tell you that I have this neutrino and antineutrino. Are they same particles? So this is, we know the properties of neutrino. Neutrinos are neutral, zero charge, massless, spin-half particles accompanying the beta particle in the decay. This is the story. Always, whenever you talk about neutrinos, this comes. And nu bar denotes an antineutrino here. Nu is a neutrino. Now, a crossing symmetry process called inverse beta decay is called, this is called as inverse beta decay. Okay, this is beta decay. Whatever I have written here is beta decay. First one, wait, let me show you an annotation. This is what is beta decay. And what I have written here is a crossing symmetry relation. Its name is inverse beta decay. That is, I take a proton plus a nu bar and E minus goes to E plus, left hand side. So this is called inverse beta decay. If I have missed it earlier, this is inverse beta decay. Now, I take this inverse beta decay And I want to check if neutrino is its own antiparticle. What can I do then? I will say if neutrino is its own antiparticle, when I put it here, P plus nu bar, I can replace this nu bar by nu itself, or I can check whether it is true. So what I will do is, existence of neutrinos was experimentally confirmed with the verification of a inverse beta decay. That is, no, this is the inverse beta, whatever I have here is discovered. P plus nu bar going to N plus E plus is verified experimentally. That gives you a confirmation of neutrino or antineutrino. We don't know that. So we have presumed that it is antineutrino, which is emitted in the neutron beta decay. Let me repeat it for you. What I am trying to say here is, my emphasis here is to say, we have said that neutron decays into a proton beta particle plus antineutrino. That is our assumption. And then I am trying to tell you, fine, it's not connected. I have not. Neutron decays into a proton plus a electron plus a antineutrino. If you don't see it, please tell me. My iScribe is not seen. Okay. Connect. Okay. Neutron, proton plus electron plus antineutrino. This is what we know. So I said a proton plus a neutrino, antineutrino, going to neutron plus E plus. This is called inverse beta decay. Name. This is what we use to verify it. Now I will ask you a question. What I will try to do now is to take proton plus neutrino. Will it give me a neutron plus E plus? Is it possible? Answer. You should answer me. When is it possible? This reaction, when is it possible? I need answer.
If neutrino and antineutrino are the same.
All right. So that's what we can try this particular process. But I have a source of antineutrinos. I don't have a source of neutrinos in my laboratory. My laboratory only has a neutron decay source, that is nu bar. If nu bar is equal to nu, I should be able to see this process. That's what is the test that is done by some people. So it is, I will tell you who did this experiment. Just a minute. This panel. Okay. I will hide this panel. This is tough part. Okay. So what it says is, we have photon, neutral pion are their own antiparticles. Now I will ask, Davis and Harmer are the experimentalists who put the question of whether neutrino is equal to antineutrino or not. This is an experimental test conducted during the year 1959. 56 neutrino was discovered, or rather antineutrino was discovered. So they considered the crossing symmetry process. Neutron plus nu going to proton plus E minus. Rather, I will show you now. What we have is proton plus neutrino goes to neutron plus E plus. That is fine. But I will take another crossing symmetry here. Neutron plus nu. Okay, let me write nu bar here. This is seen. I will take a neutron plus a nu going to proton. 1 minute. Neutron plus nu going to proton plus E plus. Is this right? Is this a crossing symmetry? From the top line, that is inverse beta decay, can I get a crossing symmetry relation like this? I want you to think.
Ma'am, it should be E minus.
No, okay, let me see. Proton is there. I have a nu bar. Nu bar is taken to the other side. Okay. It should be E minus. Correct. You are right. So I should have this kind of a relation. So if this relation is there, then I will say, I don't have a neutrino source. I will use an antineutrino source. Do I get a proton plus E minus? That can be tested, is what Davis and Harmer said. I don't know why they chose a neutron target. They had neutron target, I think, at that time. So they did that kind of an experiment. So now they took a crossing symmetry relation, neutron plus antineutrino. Instead of a neutrino, they can replace it by antineutrino, proton plus E minus. Why antineutrino here? It is because we have only a source of antineutrino. If neutrino is equal to antineutrino, I should be able to record this kind of an event. I will repeat again because if you get confused, what we have seen experimentally is proton plus nu bar going to n plus e plus. That is seen. Neutron decay is seen. So I will check this process. This is what is called as a inverse beta decay. So then I will ask, let me take what is the crossing symmetry relation, that is neutron plus neutrino giving you proton plus E minus. You should work out and then tell me this is a good crossing symmetry process. But now instead of a nu, if I replace by a nu bar, if neutrino and antineutrino are same, I should be able to see this particular process. Then I will see that is fine. If they are identical, the Davis-Harmer process should occur in nature. So then Davis and Harmer found that, I don't give you experimental details, it's only a confirmation to you. Davis and Harmer found that the process neutron plus antineutrino giving you proton plus E minus cannot be seen experimentally. They waited, they don't find it. This experiment tells you that nu bar is not same as nu. So let me repeat, this is a crossing symmetry relation. If neutrino source is there, I should have seen it. But I have an antineutrino source. If neutrino and antineutrino are same, I should be able to find this process. This is called as Davis-Harmer process. So I find that this is not seen. Okay, this is not seen at all. So this experiment established that nu bar and nu are different particles. So we don't have like pion, like charged pion or a photon. We don't have same neutrino and antineutrino are same. That relation does not hold. It's a typical thing. We should remember it now onwards. So what I will say is, you should treat a electron is a particle, and corresponding to that, I have a neutrino that is there. And E plus, this is lepton. And I can write anti-lepton associated with it. E plus is there, there is a nu bar. So that I should write anti-lepton. So my classification, like how I did earlier, I have to tell you what is my classification now. My classification scheme is for, say, I have leptons, I have hadrons, and amongst hadrons, I have baryons, and I have mesons. And baryons, you know, they are proton and neutron, and mesons are pi plus, pi minus 0, pi minus. And in leptons, I have a new electron, I have a mu minus, I have neutrino. Now, that's all. So I should say anti-leptons, they are to be listed separately. Antiparticles are listed separately. Not all antiparticles. Mesons contains antiparticles also. There is a little crooked kind of a scheme. You should get used to it. You should know what is the scheme of classification of particles. Hadrons and leptons remains. In hadrons, what are there? Baryons are there. Baryons are P and N. And mesons, they are all the pions that we have found. They are bosons. And in leptons, I have electron, muon, and a neutrino so far. And anti-leptons are E plus, mu plus, and a nu bar. That's what I should write. And anti-baryons, they form a different world altogether. Anti-baryons are pre bar, nu bar. That's what I should remember. Now I go to the next question. My question now is conservation laws. Again, continue to teach me what are particle processes. So that is to talk about one particular interaction that I have. This is called conservation of baryon number. This is a new conservation law. Again, I repeat, I had told you that we have conservation laws based on space-time. Have I connected it? I don't know, like this. Space-time symmetries, space-time continuous symmetries. I had told you about this. And then gauge symmetry for charge conservation. That's all. So now, is there anything else that I have told you so far? Discrete symmetries are talked about, that is crossing symmetry. So tell me, what are space-time continuous symmetries, conservation laws? That is just mention about different conservation laws under space-time continuous symmetries.
Conservation of linear momentum,
Linear momentum, angular momentum,
and energy.
Okay. Angular momentum. And we know to check it experimentally. That is, not experimentally, we can verify it experimentally. Linear, angular, and energy. Fine. And charge conservation is Q is conserved, and crossing symmetry does not have a conserved quantity. It's only a discrete symmetry. This is what I have told you. Now I continue further with this beyond space-time symmetries. Beyond space-time symmetry. What are beyond space-time symmetries? One thing that I observe is number of baryons in this universe. I will tell you my reason. Universe remains same. Is observation, theoretical observation, that is experimental combined with theoretical observation. I will tell you why it comes to my mind. So elementary particles are broadly classified into hadrons and leptons. Hadrons are the particles which can interact strongly. I am just bringing everything together when I talk about baryon number conservation. When if somebody asks you to write a note on what is baryon number conservation law, it's better to start like this. So hadrons are interact strongly. Leptons are incapable of undergoing strong interaction. Furthermore, hadrons are classified into baryons and mesons. Examples of baryons are proton and neutron. Antiparticles of baryon are called antibaryons. Examples of antibaryons are antiproton and antineutron. So now we will ask, question is, electron is we say that most of the elementary particles are unstable. That is unstable in the sense, there is a decay that we keep on noticing. We list particle and observe its decay. So we do see that heavier particle decay into lighter particles. We find that neutrinos and photon are stable because they are massless. They don't have any other lighter particle for them to decay into. So neutrino doesn't decay, photon doesn't decay. So it's a simplest, lightest particle which does not find anything else to decay into. So if you have any question, please ask me. Otherwise, I will just continue. Electron is stable because it is the lightest charged particle, and conservation of charge prevents its decay. That is, electron has to decay into some other lightest charged particle. There is no charged particle lighter than electron, so it cannot decay. Now question is, proton is heavy, and I should be able to find proton should be able to decay into E plus, let us say a photon. Why not it decay like that? I don't find such a decay. I had mentioned it. This decay process has still not been found in nature. So is there any conservation law which prevents it? As far as I know, that there is no conservation law which prevents a proton decay into a positron and a photon. So this is possible because proton is a charged particle and it can decay into a lighter charged particle E plus and a neutral particle photon. So conservation, charge, angular momentum conservation holds because left hand side is half integral, right hand side is E plus is half. Photon has, what spin is photon? Photon spin. Have I mentioned What is the angular momentum of photon? Have I told you? If I have not told you, please say no. Are you able to hear me? Hello, am I audible?
Ma'am. Yes,
Yes,
ma'am.
tell me. No sound.
Spin of
Half edge cross,
photon.
ma'am.
Yes, tell me. Supriya? I can see Supriya,
Yes,
Raju.
ma'am.
What is this angular momentum of photon?
H cross, ma'am.
Half edge cross.
One value, one. It's not, if you say half H bar, then photon is not a boson, it's a fermion. We have told you that photon is a boson so many times. Connect your ideas. Photon is a boson. It has integral spin of spin 1. Make a note and keep looking at it, at least to know that photon is a spin 1 particle. Okay. So once you have it, what is the right hand side spin of this process that I have written here? Right hand side angular momentum is E plus has half, photon has 1. So half plus 1 can give you what values? Half plus 1 angular
3 by
momentum.
2.
Only 3 by 2?
3 by plus 3
Half
by
and 3 by 2.
Half and 3 by 2. So you have both. That means right hand side is half integral. Left hand side is half integral. It is possible according to conservation of angular momentum. But this does not observe, cannot be observed in nature. So we have got used to it now that we have many processes. If they do not happen, there is a play of conservation law. Symmetry plays a role. So there should be a role by symmetries to prevent this conservation law. Prevent baryon number, whatever is the this process does not occur in nature. There is a play behind it. What is that play? Let us check it. So I will say absence of the decay of the proton into positron and photon suggests that possibly the number of baryons is conserved quantity. That is a guess. Why? Because what is left hand side here? Baryon. Which is a baryon? Proton is a baryon. Is there a baryon on right hand side? Is there a baryon on right hand side?
No.
E plus is it a baryon? What is E plus?
Anti-lepton.
Anti-lepton. Photon is no name, but it's not a baryon, correct? So left hand side has a baryon, right hand side has no baryon. So we will say that number of baryons may be conserved. So I formulate my law of conservation of baryon number in the following. Conservation of baryon number requires, that is, I formulate it theoretically now. Conservation of baryon number requires that we assign a new quantum number called baryon number B as follows. Why quantum number came into picture? Recall that earlier we had what is called as, let us say, charge. Charge is a quantum number for me. I will say that. Mass is a quantum number for me. What is mass quantum number? Left hand side mass, that is energy conservation. Energy is a quantum number for me. Correct? Hamiltonian has energy. Left hand side energy quantum number should match with right hand side energy quantum number. So conservation law in quantum theory means that quantum numbers should match. Left hand side and right hand side should match. So I will say if I take a proton decaying into a E plus plus photon, I will say proton has a baryon number, quantum number. People sometimes called it as baryonic charge. That is, charge is a quantum number, Q. So charge, basic charge, electric charge is
Ma'am,
Q.
we can't see the.
Okay, good. If you don't tell me, I won't know. Wait a minute. I am going it with my speed, so it is not connected. All right. Okay. Just all right. Connected. Okay. So what we called as baryonic charge. I introduce what is called as baryonic charge. I will say there is some hidden gauge symmetry. Like how I had charge gauge symmetry, there may be a hidden gauge symmetry, which we don't know so far. Hidden gauge symmetry gives you conservation of baryonic charge. So I will introduce what is baryonic charge. I will say basic unit for baryonic charge is 1. And for all baryons, all whatever I listed as baryons, they have a baryonic charge B is equal to 1. In that sense, proton has a baryon number 1. Neutron is a baryon, it has baryon number 1. Don't get confused between electric charge. For electric charge, it is different quantum number. It's a different gauge symmetry. I am introducing a new gauge symmetry, which I don't know. Space symmetry, I know. The gauge symmetries, I don't know unless I verify it. So I will say that you have a gauge symmetry called as some baryonic charge is conserved. Conserved quantity under this gauge symmetry is conservation of baryons. So I introduce B is equal to 1, like how is called electron charge is -1, positron charge is +1. Like that, I will say all baryons have baryonic charge +1, and electronic baryon under that, proton has baryon number 1, neutron has baryon number 1, or baryonic charge 1, baryon charge 1. And then I will say B is equal to -1 for proton, antiproton, and antineutron. They have baryon number -1 is what I will say. And B is 0 for all other particles. For all other particles, not baryons, it is baryon number is -1. That is my hypothesis. I am telling you a hypothesis now. Now you have to tell me what is electric charge, what is baryonic charge. I do see here that only 36 members have sent their attendance. There are 50 participants. 36 have shared their chat messages. Others who are present here, they should share their chat messages with their name. I am repeating, send your messages there. That is your attendance. If you don't send it, I will check the participant number and mark your attendance. So now I am asking you, I told you, there is some kind of a hidden symmetry called as gauge symmetry, some gauge symmetry, I don't know. Some gauge symmetry leads to conservation of baryonic charge or conservation of baryon number, that is enough for. So is it a continuous symmetry or is it a what is called as discrete symmetry? Now you should tell me. Hidden gauge symmetry, some gauge symmetry leads to conservation of baryon number is the information that I tell you. Can you decide whether the symmetry is continuous or discrete?
It should be continuous.
Because we are talking about conservation. So it is a continuous gauge continuous symmetry. Hidden gauge symmetry that I am talking about is continuous based on my information to you that we have a gauge symmetry leading to conservation of baryon number. Now I will ask you to make you sure that you learned what I am telling you. So if I say proton, what is the baryon number?
1.
Neutron.
1.
So photon.
1, ma'am.
0.
0, ma'am.
I told you 1 - 1, 0. That's all is allowed. Okay. So if I write a neutrino.
0, ma'am.
Okay. Electron.
0.
Okay. So now pion.
Again 0, ma'am.
Okay, fine. So this is baryon number. I will write a charge now. So you have to tell me what is the charge of proton. +1. Okay. I write numbers. So when I don't write numbers, I will tell you it's +1. I told you I forget about the units. I write charge is a quantum number. Its value is +1 for a proton. Its units are different. When I say h bar, that's a unit, but I call spin half particle. Spin half h bar particle is physicists' way of saying it, but quantum number is half. So that's what I will restrict myself to. What is a neutron charge? Charge of neutron.
No charge,
Zero.
ma'am.
Zero. We have a number denoting it. No charge is zero. Photon. Does photon have a charge?
Zero.
Zero.
Zero, ma'am.
Antineutrino.
Zero.
Okay. Electron.
-1.
-1.
Minus 1. So pi plus. Oh, I'm not able to show you.
Plus
Ma'am,
1.
it's not visible.
Yeah. I will tell you. This is plus 1. Charge is plus 1. E minus. Oh, it keeps getting disconnected, I think. All right. So, oh, it's gone. 1 minute. Where is this? All right. No. Okay. So what I had told you, proton, no, not written. All right, it's not getting connected for some reason. Wait for a minute. So it doesn't matter now. So I am just telling you, you have some kind of a, that is conservation laws. Just to get used to it, we have different conservation laws. No, all right, I will again invoke it. Just wait for a minute. It's not getting connected. Okay, we'll forget it. It's somehow not obeying me. So I will see why it is not obeying. All right, we will do without this thing, I scribe now. So what I am trying to tell you is, we have conservation of baryon number, which requires that proton doesn't decay into positron and photon. Why? Because left-hand side baryon number, what is left-hand side baryon number?
1.
1. For right-hand side baryon number?
0, ma'am.
So this doesn't match. So we will say there is no conservation of baryon number here. So we don't have this process occurring in nature. That can explain this process, why it doesn't happen. Proton doesn't decay into a positron and photon can be explained with the help of a new conservation law called conservation of baryon number. So we now onwards, we have to deal with a new quantum number, because certain processes do not happen in nature because baryon number is not conserved, is what we find. So I will say then that, fine, you have the baryon number conservation law. It states that baryon number after the elementary particle interaction process is equal to that before the process. So or equivalently, I will say total number of baryons in the universe remains constant. That means if a baryon vanishes, there is no such thing as baryon vanishing. Baryon converts into another baryon, no problem, but it doesn't vanish. So we will say, if there are total number of baryons existing in this universe, that does not change. Number of baryons does not change. So we write it as conservation of baryon number is written mathematically as summation over baryon number. Left-hand side baryon number should be equal to right-hand side baryon number, is what is the mathematical statement. So we say a proton decay does not occur in nature because the baryon number in the left-hand side is V is equal to 1 and baryon number in the right-hand side is V is 0. So baryon number is not conserved, hence it does not occur in nature. In fact, proton is stable against decay because it is the lightest baryon found in nature. Remember what I told you, electron is stable particle because it is the lightest charged particle, lightest negatively charged particle. There is no negatively charged lighter particle than electron, so it cannot decay. Photon is the lightest neutral particle in the sense that photon cannot decay into something else because it is massless. There is nothing it can decay into. So proton is stable against decay because it is the lightest baryon found in nature. So I will say that kind of a thing. With the help of this, I am introducing a new symmetry. So what is new symmetry? That is going to be baryon number conservation law. So now I have some exercises for you. You have to tell me which processes do not obey the law of baryon number conservation. First one. What is left
Obeys,
hand
ma'am.
side baryon? Neutron,
One.
baryon number.
1.
Right hand side.
1.
For this, it is 1.
0,
So this
0.
can happen. According to baryon number conservation law, this process can happen. First process can happen, correct?
Yes, ma'am.
So do you know this process? First process? Is it known to you? That is physics. What is this process called?
Neutron decay.
Beta decay, neutron decay, beta decay, all that. So we know it happens, but now I am verifying the additional conservation law, that is the baryon number conservation law. Now second one. Left hand side baryon number.
1.
1.
Right hand side.
1.
0.
1, ma'am.
Proton has baryon number 1. So it is
1.
1. Fine.
Whole square.
This can also happen. All right. So is this a crossing symmetry relation? Tell me. It's not crossing symmetry. It's not, but I'm writing this process. What is this process called? Can you tell me? Have you seen this process in your lectures? I have taught you. Do you see process number 2 anywhere?
Pair production.
No,
Yes, ma'am.
this is not pair production. So don't just
Neutron
memory
decay,
recall.
ma'am.
I told you Davis-Harmer relation today, correct? I taught you Davis-Harmer by whether neutrino
Yes,
is
ma'am.
same as antineutrino. This one, Davis-Harmer found that this process is forbidden experimentally. Correct? Don't get confused. Please don't get confused. I am talking about clear laws. The law says this process is forbidden experimentally. According to what? Why it is forbidden? Your crossing symmetry relation does not give you this. Okay, I try to explain if it works for me. What is happening to this? I don't know. Wait a minute, I will try, because these are very subtle things. If you don't understand, it's going to be difficult. So this is not connecting. It came. So now I will tell you. Okay, so what I told you is, first, fresh mind, think about it now. I told you neutron decaying into a proton plus E minus plus antineutrino. This is seen in nature. I told you that there is a proton plus nu bar gives you a neutron plus E plus. This is called inverse beta decay. Okay, this also occurs in nature. Now I am telling you there is a neutron. I bring this to left hand side. So n plus nu bar, nu going to a proton plus E minus occurs in nature. Okay. So now I will say n plus nu bar going to a P plus E minus. This does not occur because this is Davis-Harmer relation. Relation to verify if neutrino and antineutrino are same. Agreed? Is that fine?
Yes,
No.
ma'am.
So because neutrino source we don't have, nu bar we have a source. So if they are same, this can be replaced by this is what I had told you today. Okay. Now I am asking you, see, look here, I have given you some processes to check. What have I asked? Identify which of the processes do not obey law of baryon number conservation. That's all. So according to baryon number conservation, process number 2 occurs in nature. according to baryon number conservation. Agreed or no? What is baryon number left hand side?
1.
Right hand side?
1.
So
Conserved.
baryon number conservation allows it. But if I say crossing symmetry, according to crossing symmetry relation, does it hold? If I ask you that, I will show you. Crossing symmetry process for beta decay is n plus nu going to p plus e minus. If I replace nu by nu bar, this does not occur. This is Davis-Harmer relation. Each process that I show you has a meaning. There is some story behind each process. You have to remember the story behind it, is what I am emphasizing. Now my question, read the question and answer. First process occurs and you know it. Second process occurs according to baryon number conservation, but you know that it doesn't happen. That's additional information. Additional information is this is nothing but the Davis-Harmer relation where neutrino is replaced by antineutrino. It doesn't happen in nature because neutrino and antineutrino are not same particles. Agreed? Or no? If you don't ask
Yes,
a question,
ma'am.
I presume that you know it. You should recall it. You should understand it properly. Third process. What is baryon number left hand side?
0.
Right hand side?
0.
So this can happen in nature. According to baryon number conservation, 3 happens in nature. 4.
1.
Right hand side?
0.
So it
Not
cannot
conserved.
happen. So you should say this cannot happen according to baryon number conservation. 5.
1.
Right hand side?
-1.
So it doesn't happen in nature. So these 5 problems are only baryon number conservation. If I add to it, check whether baryon number conservation and crossing symmetry relations hold for these processes. Then you have an additional thing. First write baryon number conservation, then write what is the crossing symmetry relation for some known processes. Okay. Then you will get some additional things. These are like your questions in your exams. Okay. So I think I will stop it with this because there is additional thing. What I have to talk to you now is going to be lepton number conservation. Because people don't stop here. They will say, see, you have verified baryon number conservation. Why not be a law called lepton number conservation? It looks like we have fermion, number of fermions the elementary particles have, which are fermions, they should remain same in nature, is the idea. See, I am telling you about what are our ideas, what are our results finally, how I connect it with various results. So I will have to tell you, let me repeat it. We have stopped here with 2 things. Today's class, I told you about 2 things. One is about neutrino and antineutrino are different particles. Which is the test? It's a Davis-Harmer test. Davis-Harmer test makes use of a crossing symmetry relation and replaces neutrino by antineutrino and says that if neutrino is same as antineutrino, that particular relation should hold, but it doesn't hold in nature. So they say that neutrino and antineutrino are 2 different particles. One thing. Second thing that I told you is a new conservation law, which is a continuous symmetry called as baryon number conservation law. That is, it is a gauge symmetry. I don't know its name. Right now, I don't know its name. It is something similar to charge conservation because it's not a space-time symmetry. If it were a space-time symmetry, I would have realized it. I don't realize it. Because that I learned that charge conservation is beyond space-time symmetry. I can introduce any number of beyond space-time symmetries now, if I'm convinced that some number is conserved in nature. So I find that baryon number is conserved in nature. There should be a symmetry associated with it according to Noether's law. If a conservation law is found, there is a symmetry. I call it some hidden variable symmetry, SOME, some hidden gauge symmetry. So that gauge symmetry leads to baryon conservation law. I have told you about these 2 things. It's dense. It's quite dense. So I don't want to continue now about what I need to talk further. That is going to be lepton number conservation. That is a little longer story. I will tell you if leptons are conserved in nature or no. This is at the same time people thought If baryon is conserved in nature, lepton should also be conserved in nature, isn't it? Is what they ask. So baryons and leptons are, remember, they are fermions, that is half integral spin, half 3/2, anything is fine. They are half integral spin. We have to, when baryon number is conserved, I ask a natural question, is there lepton number conserved? Is there a gauge symmetry like that? Is what is the question that I ask, and I answer it in the next class. So that's what I will do. So if you have